Okay, so what we want to look at now is Laplace transforms. What Laplace transform will do for us, right, is we're going to be considering functions in a t variable such as this y of t over here, right? And then when you take Laplace transform of a function of y of t, where t is time variable over here, right? Then what you're going to get is a new function, big Y of s, right? So for a function y of t in time variable, when you take Laplace transform of it, right, what you're going to get is a function in an s variable, right? Okay, so some examples of functions of t when we take Laplace transform of it, right? Now this is not standard notation. I'm just using this sort of uh, ad hoc notation over here to really illustrate the fact that you're going to go from a function of t to a function of s, right? Okay, so if I have a function y of t where the y of t is just equal to t, right? Then when I take Laplace of it, I'm going to get 1 on s squared, right? Okay, so for next example, if I have a function which is exponential function e to the 2t, right? When I take Laplace transform of it, right, I'm going to get a function of s which is 1 on s minus 2, right? Okay, so your different functions of t would have, when you take Laplace transform of them, right, you're going to get different functions of s over here, right? Okay, and then, for example, cosine of 5t over here, right? If I take Laplace transform of cosine of 5t, right? What I'm going to get is s on s squared plus 5 squared. In other words, s on s squared plus 25, right? Okay, so this is an example of taking Laplace transform of some basic functions here, right? Right, so the main application for Laplace transforms is solving differential equations, right? And in particular, where you're going to use Laplace transforms to solve differential equations is when you're doing controls and so, right? Okay, so as an example, this is a course in MIT, right? Systems and controls, right? Right, so let's see over here, if we take a look at the lectures here, right? You want to notice that at some point in time while they introduce, well, actually the controls course, they start talking about differential equations, right? So ordinary differential equations, it's abbreviated as ODE, right? And they start looking at Laplace transforms in probably their fourth lecture and so, right? And what they're doing over here is you're using the Laplace transforms to solve the ordinary differential equations, right? So, and we will do that in this class, right? Given our ordinary differential equation, we want to be able to solve using Laplace transform, and that's probably the main objective for us, right? As I said, using Laplace transform to solve differential equations, right? And a lot of the theory and so in controls, so for example, say your transfer functions and so on, right? That you'd see in controls, these would be expressed in terms of this variable s over here, right? So in order to get, say, like your transfer functions and so on in controls, right? You're going to be expressing them in terms of Laplace transforms, right? Okay, so this is why in engineering you're going to be doing Laplace transforms is really for the application in controls, right? And if you're electrical and so on, they use Laplace transforms in communications and so on, right? Right, so this is our definition of Laplace transform, right? To get the Laplace transform of a function of t, right? You're going to do it via integral over here, right? So you have your function of t, y of t, to get Laplace transform of y of t, right? And this is one notation that we would use, right? The notation is you'd have y of t and you have square brackets and you're taking Laplace of y of t, right? So you want to read this as Laplace transform of y of t, right? And you get your Laplace transform of y of t by taking this y of t, right? Multiplying it by an exponential with e to the minus st, right? So this s over here is the s that's going to eventually show up in your Laplace transform. Right, so you have your function that you started off with, y of t multiplied by e to the minus st, and then you're going to integrate it, right? You're going to integrate it with respect to the time variable t, right? Now this expression over here has s and t variables, right? So it has two variables in it, s and t, right? And here we just integrating with respect to t, right? So when you're doing your integral here with respect to t, this is similar to what we did for double integrals, right? Integrating with respect to t, the s is just going to behave as a constant for us, right? Okay, and when we're going to integrate from 0 here to infinity, right? And I'd need to explain how to integrate when you have your top limit over here as infinity, right? And this is in fact called an improper integral, right? When you have an infinity like this over here for one of your limits, right? And in this case, your top limit of integration, then this sort of integral is an example of an improper integral, right? Improper integral. And so before we start trying to integrate this, I need to explain to you how to actually integrate when you have an infinity on top here, right? Okay, so this would be how you'd calculate your Laplace transform of y of t via this integral, right? Okay, now typically when you're calculating Laplace transforms, right, what you're going to be doing is you're going to be using formula, right? So for example, and the formula will come from a table such as this, right? Or if you remember, you could just, well, you take a Laplace transform where you just remember the formula, right? Okay, so you see in here some standard functions, for example, sine, right? A Laplace transform of sine would be k on s squared plus k squared, right? So it's not just sine, but slightly generalized over here. So this is, it means sine kt, right? Where the k could be any constant, well, aside from 0, right? Okay, so Laplace transform of sine kt is k on s squared plus k squared, right? And similarly, Laplace transform of cosine of kt is s on s squared plus k squared, right? Okay, I know you want to notice in these tables over here, right? What you have is, well, it's not just the function, right? It's the function, but with a parameter in it, right? This is to just give you a little more flexibility in your table, right? Because, for example, you'd want a formula over here. Let's just look at the sign, right? You'd want a formula for sine 2t, sine 3t, sine 5t, right? And so on, right? And this sine kt would encompass all of those cases, right? Okay, so when you're calculating the Laplace transform, most of the times you'd use a table, right? But I would expect you to know this definition here, right? And be able to calculate certain cases with using this definition of your Laplace transform, so integral definition over here, right? Okay, so if you want, this is similar to when you're doing a calculus and you're doing derivatives by first principles and so on, right? This is getting Laplace transform from first principles, right? But then eventually for practical use and for practical use, right? And when you say you're working in doing whatever your controls and so on, right? You're not really going to be using probably integral formula then, right? You'd probably just use a table such as this, right? Right. Okay, so right, so Laplace of y of t, the definition is via integral, right? And just some extra notation, right? So this is the function y of t, right? Notation for your function in time variable t over here. This here, Laplace square bracket of the y of t, this means Laplace transform of y of t. And the Laplace transform of y of t, when you work it out, is going to be a function of s, right? Such as this over here. When you have sine kt, right, this is a function of s, right? Remember, k is just some parameter that is associated to a function, right? So you're just thinking of this k as just a constant, right? Okay, so your Laplace transform is just going to be a function of s, right? Or if you want, in these examples here, right, notice this is just a function of s, this is just a function of s, right? So what we could do is slightly shorter notation than Laplace of y of t is to write your Laplace of y of t as big Y of s, right? Okay, so if your original function is small y of t, then the Laplace transform, what you do is you take, to denote it, right, If this is common letter, you know you use capital letter over here, and then it's capital letter S here, right? So big Y of S. So this is an alternative notation for Laplace of Y of t, right? Okay, and when you're solving the differential equations and so on, typically you'd probably use this notation over here because it's a little easier to write this down than it is to write this down. But both of these, they mean the same thing, right? It just means Laplace transform of a function y of t. Right, so as I mentioned, your Laplace transform of y of t, right? What you're going to be doing is you're going to be integrating, and your top limit over here is infinity, right? Okay, so we want to see how to deal with this top limit over here being infinity, and this is, once you have top limit over here being infinity, this is an example of an improper integral, right? Okay, so let's look at the improper integrals here, right? And you have different forms of improper integrals. For example, what you could have is you could have, say, like a minus infinity on the bottom, or other sorts of things could be happening for the improper integral. So you have different forms of improper integral. We're only looking at one specific type of improper integral that is relevant for us in the class, right? So you have top limit being infinity, and then the bottom limit over here is some finite number, right? And the case that we would be concerned about is, well, most of the cases is that this bottom limit is going to be 0 over here, right? So um, so this is a slightly more general setup than this integral here, but this will work for us, right? Okay, so an improper integral where you're integrating a function of t between a finite limit a over here and a top limit which is infinity, right? Well, how do you do this, right? Well, how you do it is for this integral over here, right? Same improper integral. What you're going to do is you're going to replace this infinity here by a r, right? And this r is going to be a real variable, right? So just a variable. And what you could do is, if you forget about this limit here for the time being, right, and you just focus on this, right? Okay, what you're going to be doing is this g of t, right, the same g of t, you're going to be integrated with respect to t, and then between finite limits a and r over here, right? So this part, just the integral alone without the limit, this is just a normal integral over here, right? Okay, and you could just work that out using your normal methods for integration. And then once you get this over here, once you work this out, right, what you will get is a function of r, right? And that function of r, once you work it out, then you're going to take limit of that function of r as r goes to infinity, right? Okay, so that's the approach, right? One sort of way to look at this is, okay, so you have this integral over here, right? If you didn't want to think too much about it, you have this integral here, right, with the r in it. When you take the limit of the r as the r goes to infinity, right? Well, then, well, what's going to happen over here? This big R is just going to go to infinity, and you're just going to end up with this case over here, right? But that is just a little bit of definition pushing, right? Okay, or next way to look at this is you have this problem with the infinity over here on the top, right? So you replace the infinity by r, and then now you're taking the limit as r goes to infinity, right? So the problem of dealing with this infinity on the top limit here, what you do is you move it off, right, into a limit, right? Okay, limit as r goes to infinity, right? So the problem with the infinity, you just sort of switch it to the limit. And the idea now is you should be able to work out these sorts of limits here, right? And we will see how to do these, right? Okay, so let's see an example of this, right? But before I start the example, just a couple more things. All right. Okay. So once this is how you define the improper integral. So as I said, what you're going to be doing is you're going to be focusing on this integral here. So you integrate this, and you're going to get a function of r, right? Now, once you have this function of r, you're going to take the limit of it as r goes to infinity, right? When you take the limit of this, if this limit converges, right? In other words, the limit exists, and you're gonna get a finite value. Then once you get a finite value, a well-defined finite value for this limit over here, then your improper integral on this left-hand side is set to converge, right? If when you're working out this limit here, right, it does not converge, right? And there's a couple ways that it may not converge, right? But if this does not converge, then what's going to happen is, well, at least what we say is that this improper integral, it diverges, right? Okay, so one more time, right? So this is my definition for improper integral. The infinity sign over here I replace by r, and then I take limit as r goes to infinity, right? So what I do is I work out this integral over here, I get a function of r, right? And now what you're doing is you're taking the limit of that function of r as r goes to infinity, right? If when you take that limit you get a finite, a well-defined finite value, right, then the improper integral here is set to converge, right? If when you take the limit, right, the limit doesn't exist, right, then your integral over here, right, is set to diverge, right? Alright, so let's take a look at some improper integrals. So these two over here, right? They may look the same, but notice over here what I have is e to the minus t here. And here I have e to the t, right? And let me remind you how you integrate exponential functions, right? Where this power over here is a linear function of x, right? So the integral of e to the ax is same e to the ax, but you divide by the a over here, right? We'll be doing definite integrals, so the c wouldn't, you wouldn't need the c, right? The constant of integration, right? And similarly, integral of e to the ax plus b, right? The formula is similar to the integral of e to the ax, right? It's going to be the same e to the ax plus b, but again you're going to divide by constant a, right? And you're dividing by the constant a that's in front of the x here, right? Alright, so we want to see if these improper integrals converge or diverge, right? Okay, and as I said, this one is e to the minus t and this one is e to the t, right? So they're different integrals here, right? Okay, so I want to integrate this e to the minus t, right? But it's an improper integral, right? So you use a definition, right? The definition, which is this over here, right? If I have an infinity sign, what I do is I replace the infinity sign by r, and that's what I do over here. So this infinity sign is replaced by r. Okay, so your infinity sign over here, you replace by r, and then what you do is you're going to work out this integral over here, and then take the limit as r goes to infinity, right? Okay, so first thing when you're doing these is you work out the integral, right? So working out this integral over here, you're going to be using this integration formula, and the coefficient in front of the t is -1. So you divide, when you integrate, you divide by the -1, right? And what you're doing is you're putting in t values. T is equal to big R and t is equal to 1, right? And when you do that, you're going to get minus e to the minus r, right? And then minus e to the 1, right? Okay, so one more time, right? So you get minus e to the minus r, and then you're going to get minus e to the -1, right? Now the minus e to the -1 would give you a plus e to the -1, which is this over here. And the minus e to the minus r, well, that's this term over here, right? So going from here to here, what I did is just cleaned it up a little bit, right? Okay, so this integral over here, when I worked it out, notice it's a function of r over here, right? And now what you want to do is you want to take the limit of this as r goes to infinity, right? So let me remind you about some things about exponential functions, right? Okay, so we're looking at, say, something like e to the at. And if we look at this number over here, this constant a here, right? So if the a is bigger than 0, so for example, this is e to the 5x, right? Variable that we're using here is x, right? Because of the graphing and so on, right? Okay, so if I look at your function e to the 5x, right? This is your graph of your function e to the 5x, right? Your graph e to the function 5x, notice e to the 0, well, you put x is equal to 0, you got e to the 0, which is 1. right? And then it just, as x increases, it just heads up to infinity, right? And very rapidly too, right? Okay, so from this graph over here, you should see, and or you should notice already, right, that the limit of e to the 5t as t goes to infinity, right? That's going to be infinity, right? Okay, and once your coefficient in front of this t over here is positive, right? Then what's going to happen is the limit of your exponential as t goes to positive infinity is going to be plus infinity over here, right? Okay, on the other hand, if I have again consider e to the at, but now consider when this small a over here is negative, right? Okay, so for example, when I have e to the minus 3t, right? Then as t goes to infinity, well, what happens then, right? Okay, so let's look at the graph of e to the minus 3x here, right? Okay, so you want to notice that when so again, when you put in x is equal to 0, you're going to get e to the 0, which is 1, right? But then, because it is negative over here, once your x increases, right? Once the x increases, your function value just starts to drop, and it basically just drops very rapidly, heading towards 0, right? It doesn't actually ever hit 0, right? You can't see it on this graph here, but this isn't supposed to hit 0, right? If you scale in, I guess, suitably, you would see that it's not hitting 0, right? Okay. Right, so, but what I want you to get out of this is if I'm going to take the limit of this function as, well, in this case, the small x heads to plus infinity, what's happening is your function values are dropping, so you're going to go to 0, right? Okay, and that is what this is saying over here, right? If I have an exponential where your coefficient in front of the t over here is negative, right, then the limit as you head towards infinity is going to be 0, right? It's the same situation as across here, right? And if you want a specific case, if this small a is equal to minus 3, then the limit of e to the minus 3 as t goes to infinity, that's going to be equal to 0, right? So let's get back to this problem over here, right? Here, okay, so to work out this improper integral, what you do is you replace the infinity over here by this big R, right? And you work out this integral over here. Notice this is just normal integration. You have now two finite limits of integration over here, right? So integrate in a normal way. When you integrate e to the minus t, the coefficient in front of the t is minus 1, so you divide by that. And then you put in your t is equal to r and t is equal to minus 1, and it'll work out to this e to the minus 1 minus e to the minus r, right? Okay, so now what I want to do is I want to take the limit of this expression as r goes to infinity, right? Okay, so you're taking the limit over here. What you could do is you could take the limit of the individual functions, right? Now e to the minus 1, e is just a constant, right? Like around 2.718, right? Okay, so 1, this is e to the minus 1, so this is 1 on 2.7, but the main thing over here is that this is just a constant, right? So as I say, what you're going to do to work out this limit is you're going to split, if you have two functions over here, you're going to take the limit of each function and subtract, right? Okay, so the limit of this constant function over here is just a constant, so you're going to have e to the minus 1, right? And now over here, what I'm doing is I'm taking the limit of e to the minus r as r goes to infinity, right? And that's really just this case here that we just looked at, right? Okay, so limit if your coefficient in front over here is negative, right? In this case, the variable is r, but it's the same principle, right? If your coefficient in front is negative for your exponential, what's going to happen is that this limit is going to go to 0, right? Okay, so what I get from this first limit over here is e to the minus 1, and then from this limit over here, I get 0, right? Now both of these integrals, they can you get a finite value from them, right? So the limits exist in both cases, right? Okay, in this case you get e to the minus 1. In this case over here you get 0, right? So this works out to be e to the minus 1, right? Okay, so this improper integral, when you work it out with your limit definition, you get the limit exists. This limit over here exists, and it's a finite value, right? So this improper integral over here, or the improper integral of e to the minus t, when you integrate from 1 to infinity, this converges, right? Okay, and it converges the value of e to the minus 1. All right, so let's see if we can get some sort of graphical understanding as to why this will give me a finite value, right? When I work out this improper integral, I get a finite value, right? Okay, so if you forget about this limit for the time being, right, what you're doing over here is you're integrating an exponential e to the minus t between 1 over here and r, which is some finite value, right? Okay, so this is my e to the minus t, right? This is your 1 over here, and I'm integrating from 1 to some finite value over here, right? So notice this is an area under the curve, right? This integral over here, when you integrate the e to the minus t between 1 and r, for some fixed r, it's an area under the curve, right? And what you're going to do now is, with this integral over here, right, you're going to let the r go to infinity, right? So letting the r go to infinity, and I'm going to scale out a little bit over here, right? Letting the r go to infinity means that we're going to take larger values over here, right? So here what I have is the big R is 1.8. If I change this to say 2, right, you'll get, notice the area over here increases, right? So when you're taking the limit, as the r increases, the limit is going to increase, right? And what you're doing over here when you working this out, right, is you taking this r over here and you keep pushing it and pushing it, and you're looking at the area that you get, right? Okay, so as I said, you're going to take this r over here and you keep moving it, and you want to see what sort of area you get, right? So if I move this to, right, I will get this area here, right? Okay, so increasing this r here, right, the area over here is going to increase, right? And what you want to notice is that, okay, so when I keep increasing the big R, right, the area is going to increase, but it's not going to increase by that much, right? Because this function is heading down towards 0, right? So the areas that you add in are very small areas, right? And in the end result, right, what's going to happen is that the total area that you would get, right, when you keep adding and so, right, would always be bounded by a certain number, and the number that is bounded by is this e to the minus 1, right? Anyway, so a rough idea, this is convergence here, right? I don't really want to get into the details, right? But this is really to just give you an idea. Because the exponential, the e to the minus t, is dropping down, right? When you're looking at the area underneath here, the area under this curve, even though the r goes to infinity, it's still bounded above, right? And effectively, well, it's a finite area, right? Okay, and that finite area is e to the minus 1. Alright, so let's take a look at a second improper integral here, right? So notice in this case I have e to the t, right? Previous example that I did was e to the minus t, right? Okay, so for this improper integral, how are you going to work it out is you replace the infinity here by r, then you work out this inside integral here, right? And then finally you take the limit as r goes to infinity, right? Okay, so working out this integral, the integral of e to the t is just e to the t, right? You put in your t is equal to r and t is equal to 1, and you subtract, so you get e to the r, right? And notice after you work out this integral over here, you just simply get a function of r, right? Right, okay, and now what we want to do is we want to take the limit of this as r goes to infinity, right? And this, okay, so, right, so we're going to take the limit of this as r goes to infinity. This is a difference of limits, so we split it up here. Right, I have limit of e to the r as r goes to infinity, and limit of this e over here as r goes to infinity, right? Now this e over here, this is just a constant, right? So the limit of this as r goes to infinity is just a constant itself, right? And I need to now contemplate this over here, this exponential e to the r as r goes to infinity, right? And in fact, I graphed it over here. This is, if you want, this is e to the r, this is your r-axis over here, and you see that as r goes to infinity here, right, what's going to happen is that the function value is just going to shoot up to infinity, right? Okay, so this limit over here is going to go to infinity, right? And then you have infinity minus a finite value, or in other words, this is just going to keep increasing over here as r goes to infinity, right? So it doesn't make a difference what this finite value is. Overall, this entire thing will head to infinity, right? Okay, so this here, this improper integral, right? You do not get a finite value over here, right? And because you do not get a finite value over here, right? This improper integral is set to diverge, right? Okay, right. And we could, again, we can get an idea as to why we have the divergence, right? So this integral over here, what you're doing is you're integrating this e to the t between 1 and a big R, and the big R is just some finite value that's larger than 1, right? So for example, over here, this is when the big R is 1.5, right? Okay, so that's the area over here. So this integral here, when the big R is 1.5, is this green area over here, right? And if I increase the big R to say 2, right? Notice you're going to get a much larger area, right? Okay, and if you keep increasing the big R, right? Your area over here, right? Which is equal to this green area over here, which is equal to this definite integral when the big R is equal to 2.5, right? You notice it's large, right? So if I keep increasing this big R over here, I'm just going to get like this area over here is just going to increase rapidly, right? So your green area is just going to keep increasing as this big R increases, right? So as I change this limit here and I increase this limit, this area is just going to keep increasing, right? And that should give you an idea that, well, if the area is just going to increase, right, as the big R increases, right, intuitively what that is saying is that this limit over here is just going to keep increasing, right, and it will head towards infinity, right? So that, if you want, is a geometrical interpretation of this limiting process here. Alright, so now we should understand how we're gonna work out Laplace transform of a function y of t, right? And if we're working it out from first principles, right? So Laplace of your function y of t, what you're gonna do is take this y of t, multiply it by this exponential e to the minus st, right? And then we're gonna integrate it from 0 to infinity, right? And this is an improper integral, and we just saw how to work that out, right? You replace the infinity by r, and then you take the you replace the infinity by r, work out that integral involving the r, and then take the limit of the result as r goes to infinity, right? Okay, so it's Laplace transform, right? When you work it out, in some cases, and we saw previously that for some cases, when you work out improper integrals, sometimes it will converge. So for example, this improper integral over here, this converges, right? And this improper integral over here, it does not converge, it diverges, right? Okay, and really the idea of the convergence and so has to do with the coefficient in front of the t, right? What you want is you want a relatively small coefficient in front of this t over here, right? You want it to be small, right? Okay, so -1 is good, right? But when it's positive, it's not good, right? And what we're going to look at is, well, -1 is good, but even better would be, say, if I had e to the -2 and e to the -3, right? So really you're focusing on this coefficient here of the t, right? And you want the coefficient here to be, in fact, be negative, and large negative values, say like -3, -5, -10, and so on, right? Okay, anyway, so we want to work out, right? So this improper integral over here, right? It may or may not converge depending on what this s is here, right? Okay, now in this class, the s values over here, we would just consider s to be real values, right? For simplicity in the working answer, right? if you're doing your controls and so on, right, this S over here, it's going to be complex, right? The theory and so for the differential equations and the formula for the Laplace transforms and so would be essentially the same thing, right? You will need to make like one or two minor adjustments when you treat an S as complex when you're doing your controls. But in this class, we're just going to treat the S as just being a real number, as I said, for simplicity, right? Okay, so let's note that, so this is a definition of the Laplace transform of y of t. It's an improper integral. This improper integral may or may not converge depending on the values of s over here, right? Okay, and your definition is that your Laplace transform of y of t, right, is defined for those values of s when you actually do have convergence, right? Okay, so for Laplace transform of y of t, right, what you're going to have is you'd see a range of values of s for which you're going to have convergence over here, right? Right, so let's work out Laplace transform for a certain function, right? So the function that I want to get Laplace transform of is e to the kt, right? So this is just an exponential over here, e to the kt. And you want to think of the small k as just some constant, right? Like 2 or 5 or something like that, right? Okay, so you want to get Laplace of this and Laplace of the e to the kt, right? And we're going to do it from first principles here, right? So we're going to use this definition, right? Okay, so Laplace of e to the kt, right? In order to work it out, we're using this definition. So where you see in the e to the k, where you see in the y of t over here, right? You're going to replace by e to the kt. So Laplace of e to the kt is going to be e to the minus st times e to the kt, which is what I have here, right? And now I'm working with this here, right? What I have is a product of exponentials, right? Okay, so this is an improper integral over here, right? But before I start dealing with the improper integral, let me simplify the inside of this integral, right? Okay, so this is a product of exponentials over here, and when you have a product of exponentials with the same base, you can add the powers, right? So I add the powers over here. What I'm doing is a little bit of rearrangement, right? Right, so I add my powers, the minus st plus kt, which is this here, right? I can factor out the t here, right? And then I have a minus s plus k in the bracket, right? Now, it's useful in this context over here to have a minus sign out in front, right? So that's what I'll do. I'll pull a minus sign out in front, with in which case inside this bracket I'd have s minus k, right? Okay, so that's how I go from this product of exponentials to e minus s minus k on t, right? Okay, so after that rearrangement, what I'm going to do now is I'm going to use my definition in improper integral, which means I replace this infinity over here by r, and I'm taking the limit as r goes to infinity, right? Okay, so now what I'm going to do here is I'm going to consider some different cases, right? Right, so I'm going to consider some different cases, right? So remember what I said, right? The small k is considered to be fixed, right? So your small k is fixed, and I'm going to consider the cases when the s is equal to k, when the s is less than k, and when the s is bigger than k, right? And this improper integral over here is only going to converge in this case when the s is bigger than k, right? We're going to see that when s is equal to k and when s is less than k, you're not going to have convergence over here, right? Matter of fact, what's going to happen is that this improper integral will give you infinity, right? Okay, so it's only in when s is bigger than k you're actually going to get a finite answer to this improper integral, right? So the Laplace transform is only, and that finite expression here, which would be an expression in terms of s, would be our Laplace transform, right? And that's only going to work when the s is bigger than k over here, right? Okay, so I'm going to split into these three cases, right? And the first thing I'll do is I'm going to consider this case s is equal to k separately, right? All right, so my Laplace transform, I use the definition of Laplace transform. I rearranged a little bit over here, and here I'm using definition of the improper integral, right? And now I'm considering this first case over here where the s is equal to k, right? Now, when the s is equal to k, right, and I want to work this out, right? If I put s is equal to k into this, right, what I'm going to get is k minus k, right, which is 0, right? So I get e to the 0, and e to the 0 is just 1, right? So when s is equal to k, this exponential turns out to be equal to 1. And working out this improper integral, right, what you do is you integrate this 1, which will give you t, and then you put in t is equal to r and t is equal to 0, which will just give you this r over here, right? Okay, and the limit of r as r goes to infinity is just going to be infinity, right? So what you see over here is that when s is equal to k, right, when s is equal to k, this improper integral is going to be infinity, right? So it diverges when the s is equal to k, right? So the main point that I want you to get out of this is uh, the convergence over here depends on what the value of the small s is over here, right? And to start off with, when the small s is equal to k, and remember the k is just some constant, right, like 2 or 3 or something like that, right? When the s is equal to k, you're in fact going to get infinity over here, right? So improper integral diverges when s is equal to k, right? Okay, and because your improper integral diverges when s is equal to k, right? What you say is you say Laplace transform it. Well, it doesn't exist when s is equal to k, right? Or your Laplace transform does not converge from s is equal to k, but usually in this class we'd use this notation, right? Laplace of e to the k t doesn't exist when the s is equal to k, right? Okay, so what we did is we ruled out the case s is equal to k, right? And now what we're going to do is we're going to consider when s is not equal to k, right? So we're looking at the same improper integral, but now we're working with the fact that the s is not equal to k, right? Okay, so we have this improper integral here, and in order to work out this integral here, what you need to do is you need to work out the definite integral on the inside, right? And take the limit as r goes to infinity, right? Okay, so right, so we work on the inside integral here, right? So which means I need to integrate this exponential, right? Now it's exponential with a t in it, and then the coefficient of the t is minus s minus k, right? So it's like this over here, where I'm integrating e to the ax, right? And then coefficient of the x is a, right? So in this case, I'm integrating with respect to t, right? And the coefficient is minus s minus k, right? Okay, so when I integrate this exponential over here, right, I divide by the coefficient of the t, which I do over here, which is minus s minus k. I still have this exponential over here, right? And then what I'm going to do is I'm going to put t is equal to r and t is equal to 0 into this expression, right? Right, now when I put in t is equal to r, right, I'm going to get e to the minus s minus k times r on minus s minus k, right? Which in fact is this expression over here, right? Okay, and then when I put in t is equal to 0, right, I'm going to get e to the 0, which is 1, right? And I'm going to get 1 on minus s minus k. But remember, when I put in t is equal to 0 over here, I need to subtract that, right? So I'm going to get minus 1 on s minus k, which gives me 1 on s minus k, right? Right, and now I'm taking the limit of this as r goes to infinity, right? Now this doesn't involve any r, right? So the limit of this here, this is just a constant as far as the r is concerned. So the limit of a constant is just a constant itself, 1 on s minus k. And now what I need to do is I need to take the limit of this e to the minus s minus k on r, right, as r goes to infinity. Okay, so what do we have so far, right? Laplace of e to the kt, right, is equal to this improper integral here, right? And we saw when s is equal to k, this is just going to work out to infinity, right? So now what we're doing is we're considering the cases when s is not equal to k, right? And to work out this improper integral, right, what you do is you work out the integral, this definite integral on the inside, right? And then you're going to take the limit of this as r goes to infinity, right? So we worked out what the integral is on the inside over here. It's equal to this expression here, right? The integral on the inside is equal to this expression over here, and then this is when you take the limit of it as r goes to infinity, right? Okay, so this limit here, right, this limit as r goes to infinity is equal to this line, right? So Laplace of e to the kt is equal to the limit of this limit here, and this limit is equal to 1 on s minus k minus limit r going to infinity of your exponential on s minus k, right? So what I have so far is this Laplace of e to the kt is equal to 1 on s minus k minus this limit over here, right? And now what I want to do is I want to focus on this limit here, right? Okay, now when you focus in on this limit over here, right, the key thing is the s minus k, this denominator here doesn't involve the r, right? So the only thing that involves the r is this exponential on top here, right? Okay, so we working with this here, right? All right, so this is exponential, this is r over here, r, and then the s and the k. The k is fixed, the s could possibly change, right? But for the time being, you could just think of the s and the k as constants, right? So this is e to the r, and then you have some coefficient out in front, right? And that's actually similar to these cases over here, right? Here I have e to the variable, and I have a coefficient out in front, right? And if this coefficient is bigger than 0, right, we talked about this, then the limit of this exponential over here is infinity, right? And if your coefficient over here is less than 0, then the limit of this exponential over here is equal to 0, right? And that's what we want to use over here, right? This limit here is gonna, what this limit is going to work out to be just really hinges on what this minus s minus k is, right? Okay, right? So if the minus s minus k over here, if it is negative, right? If it's negative, right? If the minus s minus k, the coefficient of the r, if that is negative, right, then you're in this case over here where you have negative coefficient. And if you have negative coefficient in front of the r, right, what that means is that the limit of the exponential is going to be 0, right? And this is what I'm saying over here, right? So if the minus s minus k over here is negative, right, then the limit of the exponential is 0, right? And if the minus s minus k, right, is positive, right, then I'm in this case over here like this, right? And in that case, I'll get infinity, right? So the limit that I'm going to get over here for this exponential depends on the minus s minus k, right? Whether it's positive or negative, right? If the minus s minus k is negative, then I get 0. If the minus s minus k is positive, I get infinity, right? Okay. Right, so this is my Laplace of e to the kt. We worked out so far that it's equal to this, right? And this is my limit of the exponential, right? This is the limit of the exponential. And this limit over here is when the minus s minus k is bigger than 0, right? What you're going to get is you're going to get an infinity here, right? And that's not good, right? That is, the Laplace transform is not going to exist in that case, right? Okay, so where it does exist is when the minus s minus k is less than 0. When the minus s minus k is less than 0, this limit over here will work out to be 0, right? Okay, and when this limit works out to be 0, all I'm left with is 1 on s minus k, right? Okay, so Laplace of e to the kt is equal to 1 on s minus k only in the case when minus s minus k is less than 0, right? Right, so Laplace of e to the kt is 1 on s minus k, right? Only when the minus s minus k is less than 0, right? Because in that case, this limit is going to turn out to be 0, right? Okay, so I have Laplace of e to the kt is going to work out to be 1 on s minus k when this condition holds, right? But this condition over here, right, what we could do is we could rearrange it a little bit, right? So minus s minus k being negative, right, what I could do is this is an inequality over here, so multiply both sides by a negative sign, in which case I'd get s minus k is bigger than 0, and that actually gives me that the s is bigger than k, right? So this expression over here, minus s minus k less than 0, is equivalent to s bigger than k, right? So this limit over here is going to be equal to 0 only when the s is bigger than k. Okay, so when the s is bigger than k, the Laplace of e to the kt is 1 on s minus k, because this term is going to drop out to be 0, right? Okay, so to summarize, I get Laplace of e to the kt is 1 on s minus k. but this is only true when the s is bigger than k, right? In all other cases, if you try to work it out, if the s is equal to k, right? If over here the s is equal to k, or if the s is less than k, right? What would happen is you'd get an infinity over here, right? So it's only when the s is bigger than k, right? You would actually get a finite number over here, right? Okay, and you could really think of this s being bigger than k, right? If the s is bigger than k, it means that you have, this is a fairly large negative value, right? Say like minus 10 or minus 100, right? Okay, so what this is this is like a damping factor for you, right? This would be a function values here would be small, right? And it's only small function values when you hit it against this exponential would drive the entire thing, make it small, right? And that's the key point over here, right? So for this Laplace transform to exist, you want this inside function over here to be small, right? That's the only way you're going to get a finite value when you do this improper integral. Right, so we saw that Laplace of e to the kt is equal to 1 on s minus k. That is when the s is bigger than k, right? Now this is a general formula. This is for any real constant small k here, right? So in particular, what I could do is I can use the small k is equal to 0, right? And using the small k is equal to 0 in this formula gives me e to the 0, and e to the 0 is 1. So I get Laplace of 1. And then on this side over here, I'm going to get 1 on s minus 0 here, right? So again, I'm using small k is equal to 0, right? And that's going to hold when the s is bigger than small k equal to 0, right? So when the small k is equal to 0, what I end up getting is Laplace of 1 is equal to 1 on s when s is bigger than 0, right? And you'll see this quite a bit. This is Laplace of a constant. Okay, so Laplace of a constant when the constant is equal to 1 is 1 on s. Okay, so you could also use the definition of Laplace transform to obtain this formula here, right? That Laplace of sine kt, where k is a real non-zero constant, right? Laplace of sine kt is k on s squared plus k squared, right? And you have your convergence here when the s is bigger than 0, right? Okay, now in order to prove this, you can again use your definition of your Laplace transform, right? So your definition of Laplace transform is Laplace of sine kt is the exponential e to the minus st times the sine kt, and you're integrating from 0 to infinity, right? Now this is integral of exponential times a sine, right? And this isn't extremely easy to do, but you probably would have seen this already, right? To do this, you'd need to integrate by parts twice, right? And that's what I do over here, right? Okay, so I integrate the exponential times the sine to get something involving exponential times cosine, right? And then I integrate the exponential times cosine to get something involving exponential times sine, right? And then what I do is I put this result into this over here, right? So I get an expression just involving exponential of sine, and I can solve for exponential of sine, the integral of exponential of sine, right? And then I work it out from there, right? Okay, so the idea of doing this is doing the integration by parts twice, right? If you're using complex numbers and so, right? Right, so if you use complex numbers, more specifically, if you use Euler formula, right? What you can get is you can get this identity that sine is a linear combination of exponential functions, right? Where your coefficients here, right? These are now complex, right? The j over here is imaginary j, right? Okay, and this over here, you can actually, this would be a faster way to show that the Laplace of sine omega t is sine of at is a on s squared plus a squared, right? Which is, or sine of kt is k on s squared plus k squared, right? So this result here is the same as this result, right? What I'm doing is I'm using an identity here for complex numbers, right? That comes from Euler formula, right? And well, over here, what you're doing is you're using Laplace of exponential, right? So Laplace of e to the at. But now I'm allowing the a over here to be complex, right? And that's not something I did I'm not going to do in this 2230 class, right? This is a different class where they deal with this S over here being complex, right? But anyway, there's a next way to work out this, right? A faster way to work this out rather than using integration by parts twice, right? Okay, so this particular proof, I don't require you to know this particular proof of Laplace of sine kt is k on s squared plus k squared, right? But there, however, I do expect you to be able to take Laplace transform of certain functions from first principles, especially the piecewise defined ones, and we will see that in a later lecture, right? Alright, so Laplace of sine kt is k on s squared plus k squared, right? When the s is bigger than 0, right? And what I want you to note is, okay, so sine kt, this is what this table is saying, and these are the functions of t on the side, and these are the Laplace transforms, right? So this is a table of Laplace transforms here, right? And for sine kt, the Laplace transform was k on s squared plus k squared, which is what I have over here, right? Right, so Laplace of sine kt is k on s squared plus k squared. What I want you to notice over here is that Laplace of cosine of kt is s on s squared plus k squared, right? So the formula is similar, right, for sine of kt and cosine of kt. The thing is with the sine, what you have is you have a constant on top here, which is k. And for the cosine, what you have is an s on top, on the numerator over here, right? Right, so let's recall your definitions of hyperbolic sine and hyperbolic cosine, right? Right, so hyperbolic sine of x is e to the x minus e to the minus x on 2, right? And hyperbolic cosine is a similar definition, except here what you're doing is you're taking the sum of the e to the x and the e to the minus x, right? Okay, and if you want hyperbolic sine of ax, right, or if you want hyperbolic sine of ax, all you're doing is you're just replacing in this equality over here, you're just replacing everywhere you see x by a of x, right? Hyperbolic sine of ax would be e to the ax minus e to the minus ax on 2, right? And likewise for hyperbolic cosine of ax, right? Okay, so we saw that Laplace of sine kt is k on s squared plus k squared, right? And Laplace of cosine of kt is s on s squared plus k squared, right? So you have a similarity in these formula here, right? Now, hyperbolic sine of kt and hyperbolic cosine of kt also have a similarity in the formula, right? Hyperbolic sine of kt is k on s squared minus k squared, and hyperbolic cosine of kt is s on s squared minus k squared, right? Okay, right. And then you could also compare the sine and the hyperbolic sine, right? The formula for the sine and the hyperbolic sine basically the same, except in the case of the sine, you have s squared plus k squared on the bottom, and in the case of the hyperbolic sine, you have s squared minus k squared on the bottom, right? Okay, and similarly, you could compare the Laplace transforms of the cosine and the hyperbolic cosine, right? In this case, it's s on s squared plus k squared, and in this case, it's s on s squared minus k squared here, right? Alright, so a next formula for Laplace transform that's useful for us is Laplace of t to the n, right? Okay, and this is t to integer power. So for example, t to the 0, t to the 1, t squared, or t cubed, right? And your general formula is Laplace of t to the n is equal to n factorial divided by s to the n plus 1, right? And this is for cases, integer cases, n is equal to 0, n is equal to 1, n is equal to 2, and so on, right? Okay, so let's look at some specific examples, right? Laplace of t to the 0 is, according to this formula, 0 factorial on s to the 0 plus 1, right? Now, t to the 0 is equal to 1. 0 factorial by definition is equal to 1. And here this is s to the 0 plus 1, which is s to the power 1, which is just s, right? Okay, so what I get is Laplace of 1 is equal to 1 on s, right? And this is useful to know, right? Because saying Laplace of a constant 1 is 1 on s, we in fact saw that already when we worked it out in the context of exponentials, right? Okay, if I have put k is equal to 0 in for my exponential here, I get Laplace of 1 over here, which is equal to 1 on s, right? Okay, so next one is say Laplace of t to the 1, and in the case when t is equal to 1, I have 1 factorial on s to the 1 plus 1, which is 2, right? So I get Laplace of t is 1 on s squared, right? And you can check these, right? So for example, Laplace of t squared under this formula is 2 on s cubed, and Laplace of t cubed is 3 factorial, which is 6 on s to the 4th. Right, so let's recall something called linearity, right? So what's linearity of derivative, right? And this is just derivative normal differentiation of a single variable, right? So linearity of a derivative just means that when you take in derivatives, you can break up the sums and you can pull the constants out, right? So an example of linearity would be over here, right? So if I want to differentiate x to the 5th plus 5x squared, what we do in here is, in order to differentiate the sum, you just differentiate the individual pieces, and then if you have a constant in front of one of these, you can pull them out, right? Okay, so and what we're working is here, right? But the point that I want you to make is, want you to see is that if I have a sum, or taking the derivative of a sum, you can take the derivative of the individual pieces, and you can also pull constants out, right? Now, why would you want to do that? Why you want to do that is you're breaking it up into smaller pieces, right? And in these smaller pieces over here, you just use an appropriate rule, right? So, for example, to differentiate x to the 5th, right? You're going to use a power rule, right? And likewise over here, what you'd want to do is you want to pull the 5 out, right? And then you're just left with x squared, right? And here you just use a rule to differentiate this, right? Differentiate x squared, you're going to get 2x to the power 1, right? Okay, I mean, you probably take it for granted by now, right? When you differentiate and you just differentiate in a sum, you're just going to differentiate the individual terms, right? But what you're doing there is you're using a certain property, and that property is called linearity, right? Right, and similarly, if we do an integration, right? For example, over here, I have integral of this sum x cubed plus sine x, right? Now, how would you do this? Well, you just integrate the individual pieces and then add them afterwards, right? And this again is a linearity property, right, of integration in this case, right? Okay, so linearity for integration means that I can break up the sums. Now, why would you want to do that? Why you want to do that is there's a different formula for x cubed, for integrating x cubed, than there is for integrating sine x, right? So the linearity allows you, if you want, when you're evaluating, to just break it up into smaller pieces, and the smaller pieces are easier to integrate, right? So here I can break up the sums, and linearity of integration, I can also pull constants out, right? So over here, what is done over here is that you pull out minus 5. If you want to integrate minus 5 cosine x, you pull out the minus 5, and then you just integrate the cosine x. Right, so your Laplace transform has a linearity property, right? And what that is saying is, if I have two functions of t, right, and the Laplace transform of each of those exists, right? Then if I have a sum of those two functions of t, possibly with constants out in the front of the functions, right? To work out the Laplace transform of this sum with probably constants in front here is, I can work out the Laplace transform of the individual functions, then add them afterwards. And when I'm doing that, I can always pull constants out as well, right? Now really, so this is, okay, so where does this sort of linearity property of Laplace transform come from, right? Well, Laplace transform, to get Laplace transform, right, remember what you're doing is you're doing an integral, right? So this is the function that you want to take the Laplace transform of. You're going to multiply by an exponential, right? And this exponential over here, right, times these two functions, right, would result in a function e exponential times y1 of t and exponential times y2 of t. So there should be a 2 over here, right? Okay, and notice what you have now is, what you're doing to break this up is linearity property of integrals, right? Granted, this is an improper integral, but it's the same idea as the fact that for integral you can break up a sum, right? So likewise over here for integral we can break up if it is, even if it's an improper integral, I can still, if I have a sum inside my improper integral, I can break up that sum over here, right? And this here is Laplace transform of the first function y1 of t, and this here is Laplace transform of y2 of t, right? So really this linearity property over here is coming from the fact that integration has the linearity property that you can break up sums and that you can pull constants outside. Okay, so let's see an example of using linearity to get Laplace transform of a function, right? Okay, so I have Laplace, I want to get Laplace transform of this quadratic inside here, t cubed, t squared plus 3t plus 2, right? Right, okay, so how I'm going to get Laplace of this is a sum, so I'll break up the sum into the t squared, the 3t, and the constant 2, right? But then I can also pull out, if I have Laplace of 3t, I can pull the 3 out, right? Which is what I do over here. And if I have Laplace of 2, right? 2 is equal to 2 times 1, right? So I can regard this as 2 times 1, and I pull the 2 out, right? Okay, so notice this here, Laplace transform of the quadratic, I broke up into Laplace transform of powers of t, right? And now the good thing about this is once I have it as powers of t, I can just use my formula for Laplace of t to the n, right? Which is formula for Laplace of t to the n, which is this over here, right? So I would need Laplace of t squared, so when n is equal to 2, right? Laplace of t to the 1 when n is equal to 1, and then Laplace of 1, which is when n is equal to 0, right? And I worked out all of these already, right? Laplace of t squared is 2 on s cubed, so that's I get this here, right? Laplace of t is 1 on s squared, right? And then Laplace of constant 1 is 1 on s, right? Okay, so to work out the quadratic, Laplace of the quadratic, you just break it up into the individual powers of t, pull constants out if necessary, and then just use your formula for Laplace of t to the n, right? And that gives you this, and then you just collect your answer here, right? Okay, so let's see our next example, right, of using the linearity. Now I want to get Laplace of hyperbolic cosine of kt, right? Now I told you what the formula for it was, right? But I didn't show you how to get it, right? And now we're going to see how to get it over here, right? So your definition of hyperbolic cosine of kt is e to the minus kt plus e to the kt on 2, right? And to get Laplace transform of hyperbolic cosine of kt, well, you just use the definition of what the hyperbolic cosine of kt is, right? And notice over here what you have is a sum divided by a constant, right? Okay, so you could pull the constant out, half out first, right? And then you take Laplace of the individual ones here, right? So you'd have Laplace of e to the minus kt, and then half Laplace of e to the kt, right? And now for these over here, the Laplace of the exponential, you just use the formula that you know from before, right? So Laplace of e to the kt is 1 on s minus k, right? Now this over here is Laplace of e to the minus kt, right? So in order to have a minus kt over here, right? Well, in order to get Laplace of e to the minus kt, what you do is wherever you see the k over here, you're going to replace by minus k, right? Okay, so I'd replace this k by minus k over here, right? And then when I replace this k by minus k, I'm going to get minus minus k, which is plus k, right? So Laplace of e to the minus kt is 1 on s plus k, right? Which is this 1 on s plus k, right? Okay, and then, so I have this Laplace of hyperbolic cosine of kt. I found the Laplace transform, but I can clean this up. So what I do is I take a common denominator here, right? And with the common denominator, I have an s minus k on top here and an s plus k over here. Add in over here, the k's would cancel, and I'm going to have a 2s on top. And the 2 and down here in this denominator will cancel with the 2 on top. So I'm going to have s on top here. And then I can multiply this out to give me s squared minus k squared, right? So I get Laplace of hyperbolic cosine of kt is s on s squared minus k squared, and we saw that already. Right, so what we want to be able to do is we want to be able to take Laplace transform of functions that are piecewise defined like this, right? Okay, so this sort of piecewise definition is saying, well, on an interval 1 to 2, right, the function is going to be equal to a certain t over here. Between 2 and 3, it's going to be equal to a different function, t squared. And between 3 and 4, it's going to be equal to function 12 minus t, right? Okay, so how do you graph something like this, right? Well, how you graph is to graph this here, right? What we could do is you could focus on the t here, right? So you draw your function f of t is equal to t, right? Now f of t is equal to t is just a straight line passing through the origin of slope 1, so it looks like this, right? But it's what we want is just t between 1 and 2, right? So what you do is you just chop off the piece that you want, right? Okay, and when we chop off the piece that we want, we get this piece here between 1 and 2, right? Right, and we could do the same thing. What we want is for t squared, right? We just want a piece between 2 and 3, right? So what we could do is we could graph the entire t squared, which is this here, right? But we just want the piece between 2 and 3, so we just chop that off. Okay, and the piece between 2 and 3 is this piece here, right? From here to here, right? Okay, and then finally, what we want is this piece here, 12 minus t, right? So again, you do the same thing. You could just graph the entire 12 minus t, right? And the entire 12 minus t would look like this. But we just want the piece between 3 and 4, right? Okay, and between 3 and 4, what would that be? We just chop it off. Okay, so that is what our graph would look like, right? Which agrees with the graph that I have, except probably the scale here is better, right? So you have this piece over here, right? This piece here, which is for the t, right? This piece over here, which is for the t squared, and this piece over here, which is for the 12 minus t, right? So between 1 and 2, your function is t. Between 2 and 3, your function is t squared. And between 3 and 4, your function is 12 minus t, right? Okay, so this is a piecewise defined function, right? And we just saw how to graph it, right? Now, what we want to do is we want to integrate, say, something like this, right? Now, how do you integrate something like this, right? Well, how you integrate? Remember what an integral is, right? The integral is you just you want to get the area under the curve, right? Now, what's the area under the curve here, right? The area under the curve here is this total area here, right? Okay, so your area under the curve is this total area over here, right? But what you want to notice is that this total area consists of 3 different areas over here, right? The area underneath the first piece, which is this one here. Okay. Now, this area here under your first piece, so this is your t over here. That is equal to your integral between 1 and 2, right? Okay. So okay. Right, so the integral between 1 and 2 is this first area, right, under your function. When you integrate the t between 1 and 2, you get this area here, right? Okay, and if I integrate the t squared now between 2 and 3, right, I will get a next area, which is this one here, right? Okay, so the integral of t squared between 2 and 3 is this slightly more purplish area here under the t squared, right? And then finally, what I would need is the area under 12 minus t, right? And the area under the 12 minus t is this more sort of area over here, right? And this area here is equal to the integral between 3 and 4, right? Okay, so if I want to integrate this function here between 1 to 4, right? What you're doing is you need to integrate from 1 to 2, right? And then from 2 to 3, right? So you need to integrate from 1 to 2, integrate from 1 to 2. Then you integrate from 2 to 3, right? So from 2 to 3, right? And then you integrate from 3 to 4, right? And when you add up these areas over here, you get the total area under the curve, right? Which is the integral from 1 to 4, right? Okay, so that really is to illustrate that if I have a piecewise defined function and I want to integrate it, right? How you're going to integrate is you just integrate the individual pieces over the range specified, right? So to integrate this y of t, I need to integrate the t between 1 and 2. And then I need to integrate the t squared between 2 and 3. And then I need to integrate the 12 minus t between 3 and 4, right? So your function that you started off with was in the range, it had 3 pieces, 1 to 2, 2 to 3, and 3 to 4, right? So in order to integrate from 1 to 4, what you do is you integrate over each of the ranges 1 to 2, 2 to 3, 3 to 4, right? Separately. Add those, you're going to add those up, right? Now when you integrate in between 1 and 2, right, the function between 1 and 2, the function is equal to t, right? So you put in your t over there, right? And between 2 and 3, your function is equal to t squared, so you put that in. And between 3 and 4, the function is equal to 12 minus t. So you put that in over here, right? Function is equal to 12 minus t, so you put it in, right? And once you put that in, all you get is just some nice, easy, definite integrals over here. And you work out each of these, right? And then you add it up. And that gives you your total, your integral of your function, right? And this integral over here is equal to the sum of these. And if you want well, to remind you of what I just said, right? This 3 on 2 is equal to this area here, right? The 19 on 3 is the middle area here. The 17 on 2 is the mauve area on the end on the right over here, right? Okay, so if you have a piecewise defined function, what you're basically doing is the same sort of thing as you find an area under the curve. And the area under the curve would consist of potentially different areas like this. Alright, so what I want to do now is I want to get Laplace transform of a function that is piecewise defined like this, right? Okay, so your 3 pieces here, one is between 0 and 1, right? So your function is 0 between 0 and 1, and you're seeing it over here by this dark line over here. That's to indicate that between 0 and 1 the function is equal to 0, right? Notice the function is not equal to 0 and t is equal to 1, so I have this open dot over here, right? Okay, so it's the same picture over here, right? So between 0 and 1 the function is equal to 0, and I have this open dot here, right, to indicate that your function is not equal to 0 and t is equal to 1, right? Okay, and then the function between 1 and 2 is equal to t, right? And we just saw how to do this, right? How to get this graph, right? What you could do is you just draw the entire y is equal to t, and you just chop off the piece that you need, right? Between 1 and 2, right? Notice it's equal to t when t is equal to 1, so I have this closed dot over here. But it's not equal to t when t is equal to 2, so I have this open dot here, right? And then finally, this function is equal to 0 for all values bigger than 2, right? So you want to notice that this is not a finite interval over here, right? All of these so far, 0 and 1, that was a finite interval, an interval of finite length. Between 1 and 2, that's an interval of finite length, right? But from 2 onward, this is interval of infinite length over here, right? So this is from 2 to infinity here, right? But anyway, on this interval over here, your function is equal to 0, right? And what we want to do is we want to get Laplace transform of this function, right? Okay, so we want to get Laplace transform of your function here, right? Now, Laplace transform of a function y of t is by definition an integral, right? So integral from 0 to infinity. What that means is you're integrating from 0 over here right to infinity over here, right? So you're just integrating along this t-axis here, right? Okay, so you're integrating from 0 to infinity, and by definition, you're taking this function y of t that's given to you, and you're multiplying it by an exponential, right? Okay, but this function y of t consists of three pieces here, right? And when you take your product of y of t against this exponential, right? What what that means is that this product over here actually is also going to consist of three pieces, right? Or if you want between 0 and 1, well, what is this function equal to? Right, between 0 and 1, right, the y of t is equal to 0, right? Which means that the product exponential times the 0 is equal to 0, right? So that's how you get this over here. Between 1 and 2, right, the y of t is equal to t, right? Okay, so this product over here is going to be the exponential times t, which is this. And then for t bigger than or equal to 2, right, your function is exponential times the y. But in this case, the y, for t bigger than or equal to 2, the y is equal to 0, right? So you're going to get exponential times y is equal to 0, and t is bigger than or equal to 2, right? So this function inside here consists of these three pieces, right? And we just saw that if you want to integrate something, a function that is defined in three pieces like this, right? How you do your integral is you just integrate over each piece separately, right? So for this function over here, what you're going to do is you're going to integrate between 0 and 1, and then you're going to integrate between 1 and 2, and then you're going to integrate from 2 to infinity, right? Okay, once you have it set up like this, then you really just put in your information, right? Now you can put it in from here, right? Or you could actually just skip this step here, right? And really what you're going to do is when you're working out this integral, you're going to break it up according to the pieces that you have, right? Either way it would work, right? Okay, so between 0 and 1, your y of t is equal to 0, so you put that in, and you're just going to get 0 over here. Between 1 and 2, the y of t is equal to t. Between 1 and 2, the y of t is equal to t, so you put that in also. And when t is bigger than or equal to 0, the y of t is equal to 0, so you put that in, and you're going to get exponential times 0, which is 0, right? Okay, so this is what your function is going to be. This should be a t over here. And this is an integral of 0, and an integral of 0 is just going to give you 0. This is a definite integral of 0, which will give you 0. And likewise, while this is an improper integral, if you integrate in 0 over here, it's just going to get 0, right? And the only thing left to work is work this out over here. And what you're doing is, in this case, the y of t is equal to t, right? So all you need to do is work out this integral now, right? And the nice thing about this one particular one is, because your function was equal to 0 as you headed towards infinity, right? The issue with the infinity just dropped off as 0 here, right? So now this is just a nice normal integral between 1 and 2, right? So you don't need to use any definition of improper integral or limits over here, limit as r goes to infinity. This is just normal integration over here with respect to the variable t, right? Okay, and to integrate this, you need to do integration by parts, and this happens quite a bit with these Laplace transform questions, right? Okay, so to integrate by parts, I'm going to be using integral of v du is equal to uv minus integral u dv, right? So I need to choose the v and the du, right? Okay, so choose the v to be equal to t because I'm going to differentiate the v, right? When I differentiate the v is equal to t, I get 1, right? So the idea is to get something simpler, right? Okay, and if I choose the v is equal to t, then everything else needs to be the du, right? So the du is e to the minus st dt, right? Okay, so once I choose the v and the du, to get the dv, you differentiate here, right? So differentiate the v to give you 1, right? And you get dv dt is equal to 1, and you carry the dt on the side. And over here, what you do is you integrate the du, right? And when you integrate the du here, this e to the minus st would give you e to the minus st divided by minus s, which is this here, right? Okay, and the rest of it is just following through with the integration by parts. So it's uv, right? So t times e to the minus st on s, right? And you put in your 1 and 2 in for t, right? This is your uv here. And then the integral of u dv minus the integral of u dv, so minus minus would give you this plus over here, right? You're integrating e to the minus st on s, and you pull the 1 on s outside here. And now you just integrate this here, right? And when you integrate the e to the minus st, you're going to get e to the minus st, and divide by that s, you have a minus sign, and the s on the bottom will hit this s over here to give me s squared, right? So now that I have this, I put in the t is equal to 2 and 1 over here, and the t is equal to 2 and 1 over here. And what I do here is you put in t is equal to 2 and 1, and I clean it up a little bit going from here to here, right? So there's a little bit of working to go from here to here. Or if you want, you could just check to see that this is the same as this, right? Okay, so when I put in t is equal to 1, right, what I'm doing here is I'm subtracting, right, because this is on the bottom. So I would have minus minus over here, and t is equal to 1 would give me 1 here, and I have e to the minus s on s. So I'd have a plus e to the minus s on s, which is this term here, right? And similarly, when I put in t is equal to 1 over here, right, the minus, I'm going to get a minus for this 1 because I'm subtracting here. So I'd have minus minus here, and then I'd end up with, so that minus minus is a plus, and I get e to the minus s on s squared. So that e to the minus s on s squared is just 1 on s squared, right? And likewise, you could justify, okay, so when you put in the t is equal to 2, right, you're going to get a 2 over here, so 2 e to the minus 2s on s, right? And that is 2 e to the minus 2s with the minus sign over here, so that's this term. And when I put in t is equal to 2 over here, right, I'm going to get e to the minus 2s on s squared, right? Okay, and that is e to the minus 2s on 1 on s squared minus, right? Okay, or if you want, you could just expand this out and you collect it like this, right? Why I wrote it like this is a little easier to see what's going on. It's a little neater, right? So your Laplace transform of the y of t is equal to this expression over here, right? Okay, now being able to integrate these piecewise defined functions, this is important, right? So I'd expect you to be able to do this, right? Now, what you want to notice, one last thing to observe over here is the coefficient of this s minus s over here is 1, right? And the coefficient of the minus s over here is 2, right? Okay, and if you have a Laplace transform that looks like this over here, right, where you have a e to the minus s, right, and here you have a e to the minus 2s. You're looking at the e to the minus s, look at this minus s over here. The coefficient here is 1, right? And once you see in that e to the minus s, that sort of tells you that you have a change in behavior at time t is equal to 1, right? Which you actually did over here, right? And this e to the minus 2s over here, right? The coefficient here of the minus s here is 2, right? So at time t is equal to 2, in the original function y of t, you had a change in behavior, right? Which is this here, right? Okay, so sometimes just looking at this, the Laplace transform, you can tell things about the function y of t, right? The original function y of t. And in this case, what this is saying is that t is equal to 1 and t is equal to 2. You had some change in behavior.